Hello. To predict the hourly wage using two variables, it's easy. 30 years old and 16 years in school. So you have beta 0, beta 1, and beta 2, coefficient of age and coefficient of education, and plug in. Beta 0 is minus 0.075. Excuse me. Beta 1 times age, which is 30, and beta 2 times education, which is 16. It is easy to calculate. And the result is 10.341, right? Let me show you how to do this. On Excel, there is no difference. I have three variables: age, education, wage, and the sample size is the same, about like more than 2200. And to calculate its regression results, use the same regression result. Y is wage, and X is two columns. You have to include two variables at the same time, and the first one is label. I'm going to use line fit plot. Right now the difference is the result table is the same. There is no difference, but what's different here is you have two plots, because we cannot. So we have three variables, and to draw a plot of three variables we need 3 dimension, which is impossible. So it shows a scatter plot between education and wage, and it's a predicted wage, which is for each education level. And this is ugly fitting, which shows that excuse me, just delete it. So as age distributed here, but the prediction is going up and down. So different people have different predictions at the same age. So this shows that age is not doing well. Age is like education. So the difference within the age is coming from the education. Even if you are at 35 years old, for example, still someone who have high education is predicted to be here, and lower education predicted to be here. So the difference in education causes noise in prediction. And so we have one more row in this table, because we have now two variables plus intercept plus constant term. So we have them, and as usual we get estimation results here: coefficient estimates and standard error estimates. So then think about this. So this is exactly the same result I just showed you. Then we have two variables. Constant term is usually not considered as a variable. It's almost automatically included. So we have two variables, and we learned the definition of statistical significance. In this case, which variable is statistically significant? This is a very important question, and I use 5% significance level determine which variable is statistically significant. 3, 2, 1. So remember the definition of statistical significance. We say a variable is statistically significant if we can reject the null hypothesis that the coefficient is 0, right? We assume in the hypothesis the coefficient is assumed to be 0. But if we can reject it, then the coefficient is statistically significant. It is different from 0. So now the p-value is already calculated, kindly calculated in this table. So for example, age variable has a p-value of 20.5%. So 20%, it's much larger than 5% significance level. And remember, so when I say 5% significance level, that means I'm going to reject top 5% most suspicious outcomes. But this variable's estimate happen to be top 20%. So it is not rejected. So it is not rejected, which is bad because you cannot distinguish this estimate from zero. So that means this estimate is not statistically significant. However, education's coefficient has a p-value of 0%. Most suspicious guy, so it is rejected, which means the coefficient estimate is clearly different from zero. It is different from zero, so it means something. It is something. It's not zero. It's not meaningless. So the answer is C, education. Only education is statistically significant among these two, right? And let's see the changes between this and the previous result. Maybe let me compare two results side to side. So this result, it uses only education, it uses age. Oops, excuse me. How do I show? Excuse me. So first compare the R square. R square was 10.59%, but it increased to 10.65%. Increased a little bit, very little. And coefficient, by adding age, the coefficient of education also changed, right? Even if the change is small, but still it changed. And the intercept also changed a lot. Intercept changed a lot. But intercept usually does not play much role in this analysis. So what you can see here is age is not statistically significant. So that means adding the variable will cause some changes in everywhere in the model, like R square and the other coefficient and other guys, but the change will be very small because the impact of age is very small. You cannot distinguish from zero. And like for example, coefficient of education changed, right? So like from 0.743 to 0.741. Very small change, but still it changed. So that means when you do some kind of research, including a new variable may change your result a lot if the additional variable is significant. So when you do an empirical data work, try to collect as many variables as possible and see what is important, what is statistically significant, and see how it changes, how the results changes when you include or exclude a certain variable. Right? Okay. And maybe the final final topic. It's a very interesting example. It was published in The Economist, the magazine The Economist. And The Economist reported ice cream induces anti-brain freeze. So it prevents brain freeze by eating ice cream. So make you smarter, make people smarter. So this is proven by a regression analysis between ice cream consumption and PISA ranking. PISA is educational purpose test scores. So like reading score, PISA reading score is on the horizontal axis, and ice cream consumption is on the vertical axis. Like Finland, Australia, it's a lot of ice cream. Surprisingly a lot. And United States is the third. And so so surprisingly, Hong Kong and Singapore does not consume much ice cream. Anyhow, and so go to the right means smarter, and to the left less smart, and to the top and more ice cream, and bottom less ice cream. And there is a clear pattern, increasing trend between them. It was published in The Economist. Oh, what do you think? Of course, does not make any sense. Think about this. Just stop the video, pause the video for a second, and think how you are going to refute this. Of course, it's not true. It's just April Fool's Day joke. So it was published on April Fool's Day in 2016 in the Economist. The reason is the main reason why this is wrong is because regression result does not say any causality. So in my examples, I told you as if x determines y. Actually, x determines y. It's not. It was wrong. It was a little bit of, it requires additional assumptions and additional explanations. But let me do it now. So when I say output determines the cost, it is an assumption. But that assumption is too obvious. So the causality is clear because you produce more, you cost more, right? So the causality is obvious, so I assumed it implicitly. And in the example of education and wage, also the causality is quite obvious, right? Education increases your wage, so it is obvious. However, in this example, reading score is not determined by your ice cream consumption at all. And what is the problem here? But even if they are not, even if they do not have any causal relationship, still they are correlated because a country's economic development is closely related to its education and its ice cream consumption. So the richer the country is, the more ice cream it's going to consume, and it will do better in the test. So there is a hidden variable that governs the correlation. So two variables may be correlated, seemingly correlated by calculation, but there is no causality. You cannot interpret that as a causality. Another famous example of this is pirate in the Caribbean. So did you know that the pirate in the Caribbean is correlated with the global warming, right? So as the number of pirates in the Caribbean decreases, the global temperature increased. Perfectly negatively, or nearly perfectly negatively correlated. I don't know who collects the data and who found it, but it's another important example to explain this. So you cannot interpret that as you have to prevent the global warming, you have to allow pirates in the Caribbean. It's not that. You cannot say that. So the regression result does not imply causality. Rather it only shows statistical association, and interpreting this association as a causality is additional assumption and an additional judgment. So regression model does not tell you that. You have to decide whether there is any cause and effect relationship or not. Very careful. And finally, as I said, linearity assumption is important. Linear relationship is important. We cannot handle nonlinear result. So let me show you the final example. The final example has x and y. It's simulated numbers. It's not real data. So think of this. I'm going, so you have X and Y, and there are 50 observations, 49 observations each. And when you use the regression result, you are going to get this. You will get this result. The result itself is not important. But what I want to show you here is p-value is 79%, which means it's not statistically significant at all. Really non-significant. But when you have a draw the graph, this is what you see. So the blue dots have a strong trend of inverse U-shaped trend. Excuse me. So increase here and then decrease, which is a clear trend, but a straight line is totally misleading. Straight line is nearly flat, and it looks like X does not change Y at all. Nearly has no effect, but that's not the case. Simply the problem here is that the linear regression model cannot handle this kind of pattern. Nonlinear pattern is not allowed in linear regression model. The true line is like this. This is what you have to do. This trend is what you have to find out, but linear regression cannot handle this. So that is the last remark. When you use the linear regression model, be careful. Nonlinearity can be a problem. Causality can be another problem. So be more careful in interpreting the results. Okay, this is it. I enjoyed being a YouTuber. It was really fun. Have a nice vacation, and I'm going to update homework 12 walkthrough. So do the homework and good luck. There is no exam, and enjoy a nice vacation. Bye.